but now it is. I had that same thing of claiming host, but I managed to solve it. And I've got the people's chimes turned off, so that's pretty good. We still have a bit of turnout to arrive, but I will get started. Basically, we're going to do two things today. Plus, we'll probably have time for a solid Q&A if people want to do that. The first thing we're going to do is do more on the bit setting and bit clearing, just to kind of power that home and give specific examples. And I wrote a little extra code so I don't have to write it in real time during class, where we can visualize it easier and see the bits. Strangely, printf, as you probably know, does not have a binary print format, so you cannot automatically print out ones and zeros. And I'll go over how I did that because it's a fairly, it explains some of our key concepts again. And then after the break, we'll start the dive into the chip documentation that we're using for the AT Mega 2560. And we'll take a tour around that document, which is big, and yeah, it's kind of intimidating, but breaks it down and eventually gets you what information you need. So with that, I'm going to share screen over to desktop 2, and I've got my code blocks up here. So I have sort of crafted a little handy set of tools for dealing with these binary numbers and illustrating them and making them show up, or printing them, and also entering them. So personally, I don't have hex, the higher hex codes like A, B, C, D, and F. They're just not quite at the tip of my tongue. So if I want to talk about bits, it's easier to actually type in bits. And so I wrote a little function, string binary to character, which requires an 8-bit string as an argument and converts it into a char with that pattern of bits. So we can look at how that works. And so now I can type in any ones and zeros that I want and get that char easily. And so here's a couple of examples. And another function, and I'm also going to show you the more professional way to organize a project, either in code blocks, but also in the Arduino. It works the same way, and it's really the standard that C language supports. So that is that we'll have our main, and we'll have this. Here we are going to, well, yeah, so this is still utilities to manage and mangle these bits. But we're going to put the actual utilities in another file. So this is just a file that tests and demonstrates those utilities. And then we have a .h file. If we just call a function like string bin to char, which you'll notice that's not defined anywhere in this file. So how can C know what to do with it? Well, it uses a function prototype. And for do example, which we're going to explain, here's a function, do example, and we have the function prototype up here so that C can know what to expect, know what it's dealing with when it finds a call to do example down here on line 23. But these other ones do not have function prototypes because we've put them in this other file, .h. This is, H stands for header file, and it's a header because it's at the head of the file. And C, code blocks automatically generates another folder called headers and puts, and I've pre-populated it with this file. So these are the three function prototypes for your these functions that we're going to use, um, like sorry, got confused. These functions that we're going to use, like these. So now this code is included just as if I copied that whole file and pasted it in. That's what the C preprocessor does. And then now it has prototypes for this and other functions. And then I also have, and this is main, but I also have the definition of the functions themselves in a separate C file. So here's bitset and clear. We talked about that. Binary to string converts a binary number to a string so we can print it in binary. And then finally, string binary to character converts ones and zeros string into binary so we can generate examples easily. Okay, so I have those three functions. There's no main here. And notice that we never import that file explicitly here. But the C compiler knows that we're going to start our program with main. When you start a program in C, it always begins at the first line in main. General rule. If there's and then similarly, if there's a function here which has a prototype, which it does up here, but no definition in the main file, it looks for that function. It compiles any other C files, and it looks for a definition in any other C files automatically, which would in this case be a definition down here. So as long as all the functions that are called in main have a definition somewhere, C is happy. And of course, it's doing that all the time. Like if we do say printf, printf's a function. It's got to have a definition somewhere. That's taken care of in stdio.h. That's where the function prototype is. And this bracket here, instead of a quote means look for that file starting in the current folder or the current project, which is right over here. Bracket means do not look in the current project, look in a pathway defined in the system, which goes back into the installation package of your C compiler. And there's millions of files back there in a complicated directory structure, but thankfully it knows how to look through that and find it. So we don't have to worry. And you'll see this in the beginning of almost every string C program, unless they choose to bury it into a personalized H file. So now our project, our C project is three files. It's main.c, which actually has two functions in it. You'll notice it also has do example, and then 472 binary utilities.c, and then 472 binary utilities.h. And this can be, frankly, this can be kind of a pain with C because you have to make sure this function prototype matches exactly the definition of the function in the C file. And so you have to keep those two things consistent. If you make a change in the C file, like you change some parameter to something else, then you have to remember to update it over here. Let's make sure that that's, well, anyway, that's what you have to do. And then main. So let's see what we're doing here. So first of all, let's build it, make sure everything builds. Okay, so these are the most mildest of warnings that there's a commenting inconsistency. So I'm going to definitely ignore those. And this is another extremely minor warning. I've declared a variable unsigned 3, and I never used it. Okay, what they're saying to me is I wasted some memory. I'm never going to use that memory. Okay, we'll figure out a use for it later. All right then. So or we could just delete it. So it built, and let's run it. And what do we have? So hello world, that's there. We have some test values which prove that I am accurately converting these binary strings. So let's make sure. So, well, actually, when I did this, I didn't have the ability to print the binary strings. I just said it's F7. That sure looks like F7 to me, but we can make sure. Um, although I have to store it in an intermediate value. So I think I won't bother. Um, and then down here, what we're going to do is we're going to make a new string, 11001010, and we're going to convert that. We're going to make yet another string. So we convert the test string into binary and then use this to convert it back to a string. So if we take a string, convert it to binary, and put it back into a string, of course it should be the same. And then this printf will let us verify that. So the question is, are those two strings the same? And yes, they are. So that means both of those functions most likely work. And now we're going to do bit setting and bit clearing. And I wanted to do multiple examples. So let's see what it means to do an example. We talked about this last time. We're going to use this function bit set and clear 8 with an 8-bit argument or an input, and then a bunch of bits that we intend to set and another bunch of bits that we intend to clear. And I showed you two ways to represent that. What we're talking about here is if we want to clear a bit, we have to have a 1 in that position, which is sort of counterintuitive, but both it's also intuitive because you could say where we intend to do something, we put a 1. Where we intend to leave everything alone, we put a 0. Okay, so let's go over into our code and see what that looks like. And again, I won't belabor this because we went over it. So we have a hardware register, which doesn't actually have to be a register. It just has to be 8 bits. And our set val and our clear val. And it's, I put the 8 in this name because this only works for 8 bits, but we could write another one for 16 bits that would be almost the same. It would just have different declarations. And I showed you two ways to OR the set vals in, and what am I doing here? Oh yeah, actually this is out of place, so I'll put it here. It's more like it. So first, we're going to make sure we didn't make a conceptual error here, because if I have bits I want to set and also bits I want to clear, I should never be saying, oh, I want to set that bit and also clear it, because that's pointless. So that means, yeah, it's harmless, I guess. It will just do whatever we do second, but it probably means that I have a bug, that I did something wrong. So I'm going to call that an error. So we're going to test for that, which is simple enough. If the bits are the same, if any bits are the same in the set val and the clear val using the bitwise AND operator, then this will be a non-zero value, which means the if statement will fire. And we're going to print, here's my name, and I've detected an error. You're trying to set and clear the same bit, exit. So that's going to kill the whole program, which is sort of severe, but it's one option when you detect bad input. Another option is to return an error code, but then the code that's calling this function has to detect that error code and do something intelligent. Okay, so then we're going to use the OR equals operator to set the set val bits in our temporary value, which is equal to this parameter. And then I'm going to negate the clear value bits to 0 and AND them with the test value, temp value, which clears the ones indicated by a 1, clears the bits indicated by a 1, and finally return it. Okay, so that's, we mostly went over this before, but I'm just going through it. And so this what I'm calling an example is we'll have an input, a set mask, and a clear mask. And these are all going to be strings, okay? So it's easy to type up these examples like here. So that's 3 string inputs. And so we're going to deal with them. And we're also going to have an output buffer, which is going to return a string example, or actually print a string example. And this has to be 9 because remember that every string in C has a 0 at the end, and our bits are going to be an 8-character string. So we have to allocate 9 bytes of memory, and this fills them all in with 0. Why not? Okay, so now our unsigned string 1 is going to be the input, and our we're going to call this the set mask, the mask of bits that we're going to set. Mask meaning kind of like a stencil. If you cut lettering into paper and spray paint it, you then paint those letters. That's a mask, and this is the same idea. And we're going to convert that string mask into a mask. It's a mask which is actually an unsigned. Actually, this should be char. But a short, I think, is the same as a char in our world here, but it's better to be consistent. And then the clear mask is the same thing for the bits that are going to be cleared. Probably usually need a space there, but I don't think that's a problem. And then now we're going to do the bit set and clear operation. Our input is the input, and our set mask and our clear mask. But this time it's binaries. And we're going to get out another unsigned char. And so then we're just going to print everything before with the input, the set mask that we're going to print. I'm sorry, the bits we're going to set. And I'm printing it out 2 ways here. So I generate the ASCII, the string value using bin to string 8, one of our functions. I convert that to the outbuff. So then we're going to print it as a string here and also as a hex value from its original source, just for fun. And then the clear mask, what bits we're clearing. And finally, how the data looks at the end. So that's using all these functions in a somewhat meaningful way to illustrate bit manipulation. Okay, so I compiled it and I run it. And so here we have before, that's our initial value, which indeed agrees with this. And then we had a set mask of binary 2 and a clear mask of whatever this number is. Here we're going to clear this bit right there. And so then the result at the end is correct. We've cleared the clear bit and we've set the set mask bit. And we haven't messed with any other bits. Whatever they were, they stay the same. Anybody have any questions or want any clarification about what we have been doing here? Okay, so the reason we're covering this in such depth is this is exactly what we need to do to control hardware, because we're going to have to set a specific bit in a register, but not mess with the other bits in the register or clear that bit. Just another example, just a couple other examples, just in case. We'll try this example 2, where now we're going to clear and set the same bit as if it's a mistake. building it, run it, and we get that error message because that's not a good thing. We're not supposed to do that. Okay, that worked. I'll just get rid of that and put it in the comment again. But now we'll do a more interesting example. Sorry about that. It's a spam call, even worse. We'll skip to example 3. So now, I'm just going to make up an example, I guess. The point is, this is also a buggy example. The point is that we're not limited to 1 bit. If I do that, that's actually a bug. We'll see. And let's run it. Oh, our length was not 8. Okay, we have an error check in here, which is a good thing. Over in the string binary to character, if the length of the string is not 8, we're going to reject it because that's required for what we're doing here. So I caught that. So let's just make a more complicated set mask. And we're going to clear a couple of the bits that we do not explicitly set. I think I got that right. Okay, so in our next example, we're setting some bits that are already set. 1 bit that's already set. That's okay. And we're setting a bunch of bits that were 0. And the clear mask, we're going to clear a bit that's already clear, but also clear some bits that were set. And it seems like we get a very consistent result with the arguments. All right, I'm not going to go through 3 more examples because I think we've shown it. But the point is, let's use these utilities to open and close pod bay doors just a little bit on the spacecraft. So we'll need this H file. So I've got a brand new project. I'm going to make a new project for the pod bay doors because something got messed up in there. And this is our main that we were writing at great length last time, but we didn't have we didn't use this clear enough method, in my view, for setting and clearing those bits. So now the problem is that this pod bay doors function has a main, but it doesn't have the other things project. So what I'm going to do is, I find code blocks a little confusing when you have multiple projects open. So let's be careful. I'm just going to make a new file. Actually, I'm going to see if I can put a new file in this way. Yeah, sometimes it makes the new file, but it doesn't link it to the project unless you do it explicitly. I discovered that before. Okay, we're going to make a new file. Yes. And we're going to call it the same thing. It's going to be, I'm sure I could do this by copying over, but I don't want to do that. So we got a new version of the bin utils file, and we'll just open it over here and copy it. In a real project, you would actually link the files together so you only have one copy. But I'm not enough of an expert on code blocks yet to do that confidently. We'll save it. And then here's the thing you have to do, right click on the name and add it to the project. Well, I guess it already is in the project. Okay, So that's not a problem. But which project? So we're going to close this project. Why can't I close this Oh, I'm sorry. I'm going to close this project momentarily. See, now it won't let me close the project. Oh, because these files are open. Okay, well, I'll close that file anyway. All right, and then we'll do this utilities.c as well. I'll change the name of it. And then we're going to copy them over from this file, but they're the same. Now I can close this file, and we'll close the main from the other project as well. Probably now I can close the project. Why can't I? Huh. This is not, I'm sorry about this. I just want to be careful not to mess up the other project, but we have what we need. All right. And so main.c, we're going to include binutils.h. Nicely populates that for me. It's not going to find this one yet because we never did it yet. And I don't think I want to tediously build that right now. So I think this example is kind of fizzling. But what we're going to do is, and I'll, again, what we did here is we're working on a function to open a door, a specific door indicated by this integer. And we're going to check which door it is. And we're going to get its status according to which door. And then we're going to define some set and clear bits. This is a slight change from what we had before. So we're going to, if the first door, door A, was bit 2, and well, to open it in auto mode, we had to do a 1 0. And then the second bit door, door B, was shifted over, and the third door was shifted over again, door C. So we're going to define a shift value, and then we're going to shift those bits according to which door is being operated. And then instead of using this explicit statement, we're going to go bin, wait, let me actually get the right name, bitset clear 8. And the input value is going to be pod bay door control register A. And then we're going to have the door open set and door open clear. And that's going to take care of starting the door for us. Now we're going to set the go bit. So we're going to do the same thing.
Oh, you lose audio again. Hello, Professor. We cannot hear you.
Thank you. People hear me now?
Yeah.
Okay, sorry about that. Okay, so unside chart, gore do bit, door go bit. This would be just a little better C style to make keep the constants out. Okay, so now we've started the door, and I won't keep belaboring this, but I want to expose you guys to the style of programming that's necessary when we control hardware devices. And this is going to be directly applicable to the lab when you guys start controlling hardware devices on the chip. Okay, questions, comments? All right. Okay, well, I'm going to, we may not need the full 2 hours today, which probably everybody's happy about. But I will now switch gears to introduce you to the amazing amount of stuff that's inside that little chip right there. Sorry, that's blurry. But that is your AT Mega 2560. So we'll get this document open and we'll share it. And we'll go to the beginning. Page 1, start at the top. Now it's not quite, yeah, I guess this is this a good format for your guys' screen? Font too big, font too small?
Looks good.
All right, great. So the big story here. This is just a list of all the features, and there are truly a huge number. We won't even, we'll just begin to play with a couple. But when you know how to program one, it's really the breakthrough for the others. And of course, I/O, the programmable I/O pins we're already using to flash LEDs. You can have as little as between 54 and 86 of them. I think why is there two numbers? It's because this covers a range of chips. The one we have is this one. Okay. And lots, this is substantially more memory than the Arduino Uno, and that's one of the reasons we've used this. So yeah, so we're going to dive into the counter timers in lab 2, and that's where we're going to get our hands dirty. And there are quite a few timers, multiple 8-bit and multiple 16-bit timers you can use. And these PWM channels are also the timers, so that's a little bit, that's the timers operating in specific mode. And we'll talk about PWM later, what that is. The analog to digital converters, that's going to be nice for lab 2 as well, for human input. USARTs are communication interfaces for serial data transmission. And these are frankly less and less used. They used to be used a lot. For example, plugging a old IBM PC into a modem that was external, that would be a serial communication requiring USART. Today, we usually rely on a network interface like a Wi-Fi card or Ethernet which will be different than this. SPI serial interface for that's also a serial communication. Serial meaning sending one bit at a time over a single wire, and but this one is designed for communication on a single PCB, on a single board within your cell phone. For example, for the chips to talk within your cell phone. And this is terminology that people are really rethinking, and it's really most of us now are getting to acknowledge that this is offensive terminology to a lot of people that we want to feel included in the engineering profession. So I've got a bunch of material on this in 398, but various standard groups and companies I've promised to eliminate this terminology from technology, really. And we've used it a lot in robotics, and we're changing it. We're getting rid of it. Watchdog timer, we're not going to probably use, but that's a very common thing in embedded systems that everyone should know about. And what it is that we all know that occasionally a computer can have a software bug that causes it to lock and hang. And you know, on your PC, if your PC crashes, you restart it, and that's okay. But what if your embedded system is just you know, controlling a refrigerator or something? Well, you don't want the consumer to say, "Oh, my food smells bad. I need to reset the refrigerator." That's not acceptable. So a watchdog timer is a clever thing, which is a hardware timer outside of the CPU, independent of your software, and it sends a message every so often to your computer, and your software has to respond to that message and say, and reset the timer. And if your software is dead or locked or in an infinite loop or something, it's not able to respond to the timer. And the timer knows that if it does not get reset within a certain amount of time, it will send a hard reset to the entire system and reboot the chip. So if there's an obscure software bug in your refrigerator and it hasn't been caught by all the quality control of your manufacturer, and the night before Thanksgiving, the bug occurs and your refrigerator's embedded controller freezes. And I don't mean in terms of temperature. It locks up. Some of its code goes into an infinite loop and it's just not doing anything. The watchdog timer will say, "Hey, I'm here." And then the code will not respond to the watchdog timer. The watchdog timer will do a hard reset. The embedded system will reboot, and hopefully that condition that caused the bug will not recur, at least for a few months or a few weeks, and Thanksgiving will not be ruined. Okay. That's where this power on reset feature comes in. Lots of I/O, various different packages. We don't care about that. A very nice temperature range. You could run this thing very cold and very hot, 85 centigrade. And that means it's suitable for use in industrial equipment where the temperatures could be high and low, including refrigerators. Power consumption is very low. And one thing I hope we get a chance to do, but I don't think we'll be able to do it in, especially with the COVID limitations on our equipment, is to try low power operation. And of course, you can't do much when you power down. Power is required to compute. But if you're just monitoring a sensor, which you only have to check once every 5 minutes, you can sleep for 4 minutes and 59 seconds and run for 1 second. So then you're running, you know, this is about a milliwatt, right? 1.8 volts times 500 microamps. That's about 1 milliwatt, which is a very, very small power. You're running that for a small time, and then you're running almost no power for the rest of the time. And you just go to sleep in the hardware sense. So that's very important for many applications. And we won't get to experiment with that, but we will notice that when we work with timers, there is a register where you can turn on and off all the timers, and each timer requires current. So if you don't need a timer, you can turn it off. The Arduino environment by default turns on all the timers, so they actually are turned on when we're programming them, but we could play around with turning them off, except for the ones we want to use. And I don't do that in the lab that we're going to do with timers because I'm not exactly sure which timers Arduino actually really needs for its background stuff. So I'm not going to mess with it. This is a large view of your chip, which looks just like the chip. And, you know, there's lots of pins. And these are all the pins, many of these pins, most of them are exposed in the connectors on the edge of the Arduino board. So that's what's great. Okay, so here is a very simple block diagram, joking, of all kinds of stuff inside there. I'm not going to really belabor it, but you've got a CPU in the middle, you've got flash memory, static RAM, I forgot what XRAM is, and you've got a bunch of timer counters. These are 16-bit timer counters. You've got 8-bit timer counters. This is SPI, that serial external data, and I don't remember what TWI is. JTAG is a special connector which you can apply through some pins for a special kind of debugging interface, which we do not use mostly in the Arduino world. We have A to D converters. That's going to be handy. The pins are connected to these ports in groups of 8, and they're labeled with letters. So starting with A, port A, there's B, C, D, E, F, and G, and there's a lot of pins. And those ports are the ones that you used already to control an LED in Lab 1, if you're done with Lab 1 yet. And they have, you can refer to the pins as port numbers, like pin J2 would be the second pin on port J. And if you go back up here, let's find it. Actually, port J must have a special meaning. Let's talk about port E, because I saw those pins. So port E, doesn't matter where it is in the diagram, port E does exist. There it is, right here, okay? So port E, pins 0 through 7 are the 8 bits of port E. And then if you look up here, well, E6 is pin 8, okay? And that's the chips pin. And then Arduino has yet another pin number. So we're going to learn how to trace the pin numbers all the way out to the external connector here that is easy for us to connect to. All right, and so all of these have port pin designations, and they also have names that are separate, and we'll see what those mean. So each of these ports typically has multiple functions. So like this USART, this is a serial data communications interface. There's 3 of them. Well, there's 4. There's 0 and 3. And when they break them out like this, it means they're in they have slightly different features. And of course, serial communication is an external function, so it needs pins. So it can use the pins in port J. So in general, each of these pins has multiple functions, and typically you can only use one function. So you have to sort of throw away some capability of the chip once you pick a function. But there's so many, nobody uses all the features of this chip. Okay, so various comparisons. Here's a description of the ports. Here's an architecture overview. I've already gone over some of this in conceptual terms Monday, but this is the specific one for our chip. So the ALU is that ALU, just like I described. And then we have a more direct pathway. The data from the registers does not have to go right on the bus to the ALU. It has a hardware path, so that's faster. And so you can do any operation on any pair of these 32 8-bit registers. An 8-bit data bus. Many of these are 16-bit registers, though, so they clock their data in 2 cycles. SRAM, static RAM, means random access memory that holds its data as long as the power is on. And the EEPROM, where we could store some data that comes back when you power it back on. All our IOs and so forth, you can study this. And there, of course, I'm not going to take you page by page through 600, and this is a total of, oh, I guess it's only 422 pages. I thought it was 600 for some reason. I've been using that number. So some highlights. So external memory, you can plug a memory chip onto the output bus of this board. We are not of this chip, and Arduino designers did not do that. So they are not, there is no external memory. So we'll skip that. The clock is a clock, power management, system control, and reset. Let's start with I/O ports. This is a very important pin right here. I'm sorry, a very important graphic right here. So this is a very general simplified schematic of all the I/O pins. So there's a pin that's accessible to you by tracing it to the correct connector pin on the Arduino board. And so here's the schematic. So what are we talking about here? Well, first of all, there's diodes. These are very nice to have. This goes to the power supply, and this is ground. And what does this mean? Well, what it does is it protects the logic from putting to a degree. Okay, so you still have to be careful because it's still possible to blow these pins out. But we have the protection of these diodes. So let's say that the power supply is 5 volts and you put 7 volts on this pin. That will destroy this logic, except the diode conducts, it's now forward biased. And so the highest this gets to is 5.7 volts, the forward bias voltage of the diode plus the 5. So, and this hopefully is protected at 5.7 volts, it's still safe. Similarly, if you go to a negative voltage, this diode protects your input. Then we have a capacitor. This is not really a capacitor. It's just the capacitance of the input to the chip. And the wire, there's a little tiny wire that connects to the chip inside the chip. And the pin itself is a plate of metal, which has some capacitance. So they didn't design a capacitor in there because that does slow things down. They're trying to tell you that despite our best efforts to eliminate it, there's a little bit of capacitance in there and you should know about it. And you could read the specs for what it is. We don't need to worry about it for the speeds that we're using. And then there is the logic which reads the input. We'll see a lot more about that. This can also be an output. So the output can drive this pin if this is selectively changed to an output. So every pin we can decide, is it going to be an input where we read its value, or is it going to be an output and we can set it. And then the pull-up resistor. So the pull-up resistor is only used in input mode. And what this does, this is basically, this MOSFET is just a switch. And again, up here is the power supply. So what's going on? Well, you can configure a bit in a register to turn this on and off. And typically we'll set it and forget it for the entire program. And what it does is it allows you to sense things that maybe can't pull the output all the way up. So the most common example there would be a switch. So if we want to have a switch and the user can flip the switch and our software can read the switch, we connect the switch to here and we connect the other end of the switch to ground. And then what happens? Then we enable this pull-up resistor. So if the switch is open, the pull-up resistor makes a good quality logic 1 signal right there, and we read a logic 1, and we know the switch is open. If the switch is closed and this point is grounded, then current flows through the resistor to ground, and this point becomes logic 0. And this resistor is internal to the chip, and they've designed it to work that way so that we can connect switches or contacts or similar sensors to the chip without any other resistor. It's a convenience, nice feature. And this is optional. You can turn it on or turn it off. This is the real thing under the hood. There's much more, okay? But I'm going into detail because you're going to use pins. You're using pins already, and you're going to do a lot of things with the pins on these chips. So for every one of those 50 pins or whatever it is, you get this. And I'm not even going to tell you everything about it. I don't even understand everything about it. But we just went over this part, okay? That is the pull-up resistor. And this is a bunch of logic that determines if the pull-up resistor should be set or not. And these bits, well, we have some registers that control bits that are these inputs to determine how the port is used, how the pin is used. So if it's an input, by the way, these two circuits here are when the pin is an output, because you can see this is an output. This little triangle is a driver, which amplifies the logic value right here. And this logic allows the software to set and hold that bit. This is a bit in a register. It's a D flip-flop, just like we showed. And then down here is the channel in input mode, where we can sense this voltage and read it. And this is I think this is protection circuitry, and we can turn it off during sleep mode and stuff like that. I'm not even sure what this synchronizer does, but the simple version is that if we read this bit, we get the value of it on the data bus. And and then there's a bit called the data direction register, which sets whether this is an input or an output. If it's an output, I think you can still read it, but that's a little bit meaningless. So there's these 3 bits, the data direction bit, which is input versus output, the port bit, which is the value itself, and the input bit. And the port itself, that pin, can be in these configurations. So we have the data direction registers, maybe the most important one. You set it at the beginning. 0, if you set it to 0, if you set that bit to 0, and you don't have to set the whole port, you can set individual bits, then it's an input. So all these states are input, but they're slightly different inputs. So you can have the pull-up resistor. In this case, it's the this is the pull-up resistor bit. And in output mode, the pull-up resistor bit is not meaningful, so we put an X there. In input mode, if it's a 0, the pull-up resistor is connected. But if this is a 1, it's not connected. It's a high impedance mode, meaning as little current as possible flows into or out of the pin. And that's also true of this mode, 0, 0. So these are identical modes, actually, depending on the pattern of these bits. Okay. This is very low level. We don't have to worry about it at our speeds. Also, they have this sort of scary thing that you have to read the port, a 16-bit port in 2 phases, and here's assembly language, and it's 2 steps and so forth. But fortunately, C takes care of that automatically. And to read, for example, reading some pins is that simple. So this statement I equals pin B says read all the 8 bits of port B into the value I, and that's it. So I'm going to take a water break. I think I'm going to just power through for another few minutes, and then we'll quit without taking a break, but we'll quit early. Okay, so again, all of this stuff, and we're going to work through examples on how to set up those pins and so forth. Interrupts, we're going to be talking about a lot, but we haven't introduced the concept in detail yet. So these are standard locations in memory where you put some code pointers to do interesting things. And then we get to the timer counters. So here's an 8-bit timer counter. As you can see, it's a pretty complicated system. And basically what we have is some logic to control it, a clock input, and the clock can be an external signal. This is a pin here that you could wire up. Like suppose you want to build a frequency meter to measure the frequency of a signal. You would take your external signal, maybe analog massage it a little bit, turn it into a logic square wave, and stick it in here. And then your timer counter could be counting how many pulses you get for a fixed period of time, and you get the frequency. So that's an application. Of course, the chip itself runs on a clock, which is 16 megahertz. And so the other purpose of timers is to count a known clock to measure an interval of time. And there's a thing called a prescaler, so that we don't always have to use the 16 megahertz clock. We could use an 8 megahertz clock. We could use a 4 megahertz clock, and we could divide it down to have slower counting if desired. Okay. And then this is the actual counter itself, which is 16, well, in this case, 8 bits. So it can count from 0 to 255. And then it repeats. And And it can go up and down though. So there's some control logic which could tell it to count up or count down, or count up and then start counting down and then start counting up. Lot of capabilities. And then I think I can detect that now because there was like a slight change in my static background. Anyway, hopefully you can hear me now. Show of hands if you cannot. But at any rate, then this is the comparator. And this is another comparator. And this has an important function. So I may want to count not to 255, but I may want to count up to, I don't know, 187. So I can write 187 into this register. And then when the counter equals 187, that event is transmitted through this signal here to various places. So in certain modes, it could cause the counter to clear itself or change direction. And it can also be used to generate an output. And that's another output pin. So, and furthermore, often it will be used to generate an interrupt. And again, we're going to go much more into interrupts, but this could be used every so often to stop your software, start a little thing happening, and then return to your software. That's what an interrupt does. And there's many, many modes here. So it's extremely flexible, perhaps too flexible. And this, there's a very detailed explanation of what every register does and what the modes are that it operates in and so forth. But it takes careful study and digging into it. Okay. And again, they go into quite a bit of detail explaining each of these things. So you really never have to guess. That's the benefit of this kind of documentation. It's dense, it's long, it's extremely complete. And they know how to do that. All right. And then these are some things that show the modes they're in that you can have. And so this is the count. And so it's counting clock pulses furiously, and the count is increasing. But then it gets to a certain level that you can program, and it drops again and counts and drops. And you can make the output toggle, that is, it change state every time the counter hits 0. And so you can make a waveform, for example. And we're going to do that with our tones instead of explicitly counting the time in software. If you change the value where it resets, you can make the frequency faster, for example. And you can generate what's called pulse width modulation. I'm going to have more to say about that, so I'll skip it here. And there's timing diagrams, and these are the registers. So I tried to sort of copy this with the pod bay door thing. And so these are the 8 bits, and these are what they mean. And dash means nothing's used there. It shows you this is a read write bit. And then this tells you exactly what those bits do. So here's like for control register A, for output A. So the timer, you got to keep referring back to this diagram. Way back here. So it has an output A and an output B. This has 2 outputs, okay? And you can have separate triggers for the 2 outputs. So that's kind of cool, even if it's just one counter counting. And then getting back to where we were, and nicely, they have clickable links that help you go back and forth in here. But here's the output compare mode, and that could be for both A and B. And then it tells you For example, toggle the output when the compare matches, or clear the output when the compare matches, or set the output when the compare matches, or don't do anything with the output. So those are your options. And so that's all we'll take on the deep dive. Then you get your 16-bit counter, which is just a super duper version of the 8-bit counter, but gives you much higher, as you know, much higher counting resolution. You get 65,000 count values here. So you can, for the same amount of time, you could have much finer accuracy and resolution. You also get 3 outputs with these instead of 2, and other interesting features. So like it has some processing features for trigger comparator inputs. So you could have a noisy pulse come in from a sensor, and you could process it with this noise canceller and so forth, and edge detector to get more reliable operation. And then as this thing's counting, you can freeze it and store the value exactly when a pulse comes in. So you could measure the timing of an arrival pulse very, very accurately without any software delays. That's all done in hardware. And so you could use that to make an extremely accurate measurement of when a pulse arrives for LiDAR, radar, sonar, or something like that. Okay. So yeah, so we have all those timers. We have SPI, which is the way to communicate with external devices through these 4 pins, which is a clock and a strobe and an input and output data streams. And there are many chips that know how to talk SPI. And I don't think we're going to dive into detail on programming this, but I reserve the right later. I'm not sure. I don't think so. Useful things, analog comparator. So you can have different analog values come in and compare them to a specific voltage. Always important, analog to digital converters, 10-bit resolution. That's a little bit low these days for some of these embedded chips. Of course, that gives you 1,024 values, which is a lot, but it's not going to give you high fidelity audio digitizer, for example. This similar documentation. Some features, again, we aren't going to use our JTAG. So JTAG is a 4-conductor standard for development systems to do things like halting code and injecting breakpoints and inspecting. Arduino does not use that, so we don't. Is basically what it boils down to. You make the decision whether or not to use that kind of when you design your board, and if you want to expose the pins to allow that to be used. Bootloader support. So this has to do with the software that allows code to be uploaded into the chip. And again, we can thank Arduino for worrying about this, and we don't have to worry about it. But there's a little bit of code flashed into that chip that handles that handles the data when we upload our code into it. There's some valuable stuff down here, like the register summary. So this is a huge thing of all the registers in the chip and what all the little names are for all the bits in those registers. And so obviously you're not going to read this for entertainment. What happens though is, what I've found that's cool is this is a well-indexed PDF. So let's say I'm going up, and here's a kind of pro tip. So let's say I'll use the table of contents, 16-bit timer counter, and I'm working on this and figuring something out, and it's like, gosh, OCNB, I'm on timer count. N is the number of the timer counter that you're using. And so let's call it timer counter 1. And I want to know everything I can find out about that pin OC1B. So if I search Control F OC1B, whoops. And I'll, okay, well, I can't believe that's not in there, because there is a pin for it. Oh, actually, that's the reason might be that this is, I know there's a 4, because they don't have, no, they didn't find 4 either. Wonder why that is. Well, let's try NB. This is still a handy, okay, oh, I know what I did. I put a 0, not an O, okay? OC1B. All right, now the point is you'll find references to this throughout the document, and you never know which page is going to give you that key information you need. Now, this is a false alarm because FOC1B is not the same. Okay, now I just learned that OC1B is pin 25 on the chip, and I can go into the schematic and there's a document in the lab write-up that walks you through this process, going through the schematic and finding where pin 25 goes in terms of output pins on the Arduino. Let's see what else we find. Oh, that's a different package. Okay, so this is important too, because this says that the pin PB6, which is at 25, it has different functions, including OC1B, but also PCInt6. So it's an interrupt that we could set for pin change, whatever that is, but it's another function. You can see that pin PB7 pin has 3 functions. Okay. Here's a little more description of it. So anyway, definitely use the search feature when you're reading stuff in this document, because it will help you. Now here's more like where we're using it. Okay, so that was this register summary, and I think those are main highlights I'm gonna leave you with. So I'm gonna turn it over again for questions. Let's go with wide open questions. First, questions on this stuff, and then any question. Everybody's happy. All right. Well, as always, keep the questions coming on Piazza, and we'll try to stay on top of them. And let's see, there's a chat. Will I upload the code to Canvas? That was an old question, but I now see it. Yeah, I will. You can see that code and play around with it. All right, so I will see you guys next week. And the lab, I think it's lab 1. Yeah, lab 1's due Sunday night, so make sure to stay on top of that, and don't put it off completely to the weekend, because it'll be harder to get Q&A support on the weekend. That's just my advice. So thank you very much, and I'll see you soon.